Hello, welcome back to my series on implementing the ASBoot, a custom bootloader for ARM microcontrollers. In this episode, we will be covering the process of parsing the master boot record, and I will be providing a time-lapse of the implementation. So, by watching this video, you will gain an understanding of the master boot record and its role in the booting process. As always, it's a diary of progress about ASBoot implementation, giving you an inside look at development process. So let's get started. We have a CPU connected to some RAM memory, where the processor reads and writes binary data. The RAM memory is volatile, meaning its contents is lost when the device is powered off. On the other hand, non-volatile memory, such as a hard drive, retains data even when the device is not powered. Of course, the processor is exchanging some binary data also with it. A hard drive consists of disks that are split into cylinders and then sectors. Let's number some of them. Other types of non-volatile memory, including solid-state drives made up from memory blocks, and NOR flash, which is used in our project. All of these types of memory can be represented as linear memory. I'm marking in green the first sector of each device, and this sector may contain MBR. In our project, we are using NOR flash. So let's simplify that diagram to show only the parts on which we are working to implement MBR parsing. So we will represent the drive as an array of sectors with a fixed size of 512 bytes, which is common unit for hard drives, although other devices may use different sizes. For example, our NOR flash is using 4 kilobytes. So as I said previously, the first sector of drive may contain the master boot record, which describes the disk layout and contains code to boot the computer. In most cases, this code initializes the system and jumps to the next part of the code located elsewhere on the drive. The first part contains the boot code that I just described. It's followed by a partition table with 4 master partition descriptions. And at the end we have magic number that confirms that we are dealing with MBR sector. These blocks have a predefined size. The boot code taking up the first 446 bytes of data. The partition entries taking up 16 bytes each, and the magic number taking up 2 bytes. Summing up, we have 512 bytes, so it's exactly the size of the sector. Partition entries contain useful information, including a bootable flag that tells the bootloader that a specific partition contains software to be loaded. For example, let's mark partition 3 as bootable. Let's modify diagram to fit into the RP2040 booting process. The difference lies in the boot code, as RP2040 does not follow MBR scheme. However, MBR can still be used by splitting the boot code into sections for RP2040 second stage bootloader and bootstrap code. RP2040 itself does not use the partition table, but the ASBoot will do it instead. So we have a second stage bootloader with 252 bytes, followed by 4 bytes of checksum and 190 bytes of bootstrap code. The RP2040 bootloader embedded into core copies that 256 bytes of the first sector from the drive to RAM memory and runs it if the checksum matches. That code initializes flash memory to support execute in place mode and jumps to the bootstrap code, which is needed to execute the ASBoot. To understand how RP2040 deals with the drive using my implementation, let's check out the next diagram. For the sake of this explanation, I added an array of RAM memory mapped at the address shown above it. An example layout may look like this: MBR followed by ASBoot code, size is not defined yet, and then partitions described inside MBR. Let's mark one of the partitions as bootable, which will contain some file system. What file system will be supported, we will see in the next episode. inside it there will be an application to be executed, such as the kernel of an operating system. So how to execute that kernel.bin? Firstly, we have to find the partition in the MBR. After that, the file to be executed must be found inside the file system of that partition. And if found, we have two options on RP2040. Option number 1, we can execute the binary in place by just jumping to the address that it's built from RP2040 memory mapping and physical address on that drive. The other option is to copy that binary from physical drive somewhere into RAM memory and then jump to application inside RAM. To complete our knowledge about MBR, we have to also touch the partition entries. Each entry contains a status flag that marks the partition as bootable or not. This field is followed by CHS address of the first absolute sector of partition, which is an old way of describing data start and data end encoded based on the physical hard drive layout. That field is followed by the partition type, which may describe how to read data from the partition. The next field contains the CHS address of the last sector of that partition. However, instead of using CHS addressing, we will be using the new one, logical block addressing, which is a simple one, where those fields just contain sector numbers for the beginning and end of partition. That's enough theory. In your computer, the MBR looks almost the same. But nowadays, your computer probably is using GPT layout instead of MBR. Now it's time for implementation, so go get some coffee! To begin with, I developed a MBR parser library and also included a draft of the MBR structures, as explained in the theory section. Then I used that library and implemented first function that validates MBR, this magic number at the end of the sector. Then I created a virtual drive, which was fairly easy in Linux. I used the dd command to create an empty file and then use a partition manager like fdisk to create an MBR. As we can see, I created 3 partitions with the second one marked as bootable. To be able to read the drive, we need to extend the hardware abstraction layer to support disk operations. For this part, we only need to implement the read function. In practice, reading from a block device may not support reading single bytes. However, all currently used hardware support this. NOR flashes, for instance, supports reading single bytes, but Iris is block-based. This is why NOR flash can be used to execute in place. Alternatively, NAND flash only supports block reads. Regarding our host implementation, it may support whatever we implement in the simulation. For simplicity's sake, I will make it as straightforward as possible and just copy the virtual drive to RAM memory. However, for compatibility with future hardware, the disk abstraction uses sector-based reading. The implementation will take the path to the virtual drive as an environment variable and copy the entire contents to vector of bytes. For now, I'm using hard-coded 512 bytes as a sector size. But in the future, it should support real size of sector for particular device. I added some logging for verification and testing purposes. Also, that dump memory function is used to verify that we actually read bytes that we expected. Output formatting is essential for the function to be useful. As you may have noticed, I'm using an external library called EUL. This library replaces STL functions to be smaller and without heap memory allocation. It was specifically created to meet the needs of embedded software development. Here is the final implementation of the MBR structure, which follows the classical MBR since I'm not interested in the bootcode part from YaSBoot's perspective. Please note the use of the packed attribute. It's necessary to enforce the memory layout as described in the struct. Otherwise, the compiler may add padding to align the memory for better performance. It's important to note that all fields in the MBR structure are in little endian byte order. This means that the least significant byte of each field comes first, followed by the next least significant byte, and so on. It's crucial to keep this in mind when working with the MBR structure, as interpreting the fields incorrectly could lead to errors or unexpected behavior. After executing the host implementation, we can confirm that the MBR was parsed successfully. My next step is to extend the implementation to support MSPC. Fortunately, thanks to whole implementation, we only need to implement disk abstraction to achieve this. With this in place, we can move forward with additional functionality and ensure that our system can support all necessary operations. At present, MSPC only supports reading from the main memory map drive. This is sufficient for our current needs, as support for the other devices will be added in the future. As I was working on previous episodes, I broke binary generation for ARM processors. Now it's time to fix it. Let's attempt to execute the binary on real hardware and see if it runs. However, we should expect the MBR validation to fail at this point, as we have not yet programmed the image with MBR information. Great, we have information that drive contains invalid and dump of memory because magic number not matches. We need to change the way we create the image for MSPC hardware. To illustrate this, let me show you a diagram. Previously, we created a pure binary with the YaSBoot implementation, which consisted of two parts, the RP2040 second stage bootloader and the YaSBoot binary code. In the new approach, we will create an empty image and then use a partition manager like fdisk to create the MBR. Next, a new script will be used to fill the RP2040 second stage bootloader inside the MBR bootcode. Of course, there will be some partitions defined by the MBR somewhere on the drive. The final step is to use the script to place the YaSBoot binary between the end of the MBR and the beginning of the first partition. I created a Python script called write_YaSBoot that uses the external library PIMBR. Let's try out new image on MSPC hardware. Since we introduced a testing environment in previous episodes, let's add some automated tests to verify for regression. To prepare the data, I use a hex editor to make changes to the testing images. I have created two tests to verify the correctness of the code. The first test checks if the parsing of a correct MBR is successful, while the second one checks if the code reports a failure when a MBR is not found. I have disabled the memory dump on failure since this feature is only intended for testing and debugging purposes. After the initial tests, I extended the implementation to search for a bootable partition. I have also added corresponding tests for this functionality to ensure that it works as expected. That's it for today's episode of MSPC development series. I covered a lot of ground, starting from MBR parsing towards searching a bootable partition. I also changed away how I'm creating images for MSPC board, and now I'm applying full images of Drive. Also, I added some tests to verify that implementation is working correctly and to ensure that in the future there won't be any regression. Leave your feedback in the comment about the series and any suggestions that you may have for the future episodes. As always, thanks for watching and learning with me. See you again in 2 weeks with more MSPC development updates. Bye for now!